Alright, so the well, first half, what we're gonna do today is we'll just talk about syllabus stuff, do pretty standard stuff. And then we'll get into some review and kind of like change applications. It's not really that the material is different, we just use a different frame of view. For some of these ideas, when it comes to bonding and things like that. But first things first, so the structure of the Canvas shell look like this. I'll change which one of these buttons is highlighted as we go through, so you always know what week we're in. I don't usually get to that till Tuesday morning. If I have class with you on Tuesday morning, I'll probably update it on Tuesday mornings. But then I will, you go into any of these pages, always put the slides, the PDF ahead of time, depending on when I get it done, usually about half hour to 10 minutes before lecture starts. I'll get them uploaded so that way you can have them up. If you want to take notes on the slides themselves, or just have them up so that you can flip through them as I'm teaching as well. And then what I'll do for this classroom, what works best is I'll basically just do a screen share on Zoom and record the screen share. So your voices will be on the recording, but you won't be on the recording. And then I'll just upload them to YouTube and then link it here. Whenever it gets done processing, which is usually sometime this afternoon. And so I'll just keep filling things in as we go. If you go back, if you click ahead right now, I haven't gone through and cleared out all the old links. And so I just unpublished the other pages. So you'll just get a week it's not ready yet. If you see this and it is that week, I just forgot to hit publish. So shoot me a quick email and I'll take care of that. Other than that, any announcements or anything like that, you make sure you have your notifications on if you use the Canvas app. Because that's how I'm not really gonna send emails, I'll usually just push an announcement. So if there's a weather issue or if I'm sick or anything like that, or if we need to cancel class for any other reason, I will make an announcement. And that'll also include there's a couple assignments where I would need to provide you with data for you to then analyze. I'll usually just make an announcement and attach it there, and then I'll also attach it to the assignment itself. And then the assignments, I'll try to keep these links updated, but sometimes I forget. So you can always just go to assignments. And this should all look really familiar to you. I have tentative due dates in there just so it shows up in the syllabus page correctly and in the right order and everything. But obviously they're just tentative if we need to change anything on these dates. Some of the labs have taken 2 weeks in the past, but sometimes they only take 1 week, so there'll be some flexibility. And that also, the syllabus is up here as well. There's a PDF copy of it, which is kind of how I recommend it, but they also require us to put it in as a copy and paste our syllabus formatting into Canvas. This is the way I always look at it. And again, these are tentative dates and chapters. So there will be some movement within them, but just if you're planning ahead, I'm gonna miss this day, what lab is that gonna look like, that sort of thing. Got a basic idea of what's going on there. Oh, these chapters, we're not going to go strictly in order according to our textbook. Our textbook for this class is linked on Canvas. It's on gonna fix that. Not gonna even let me click now. It's linked on Canvas. It's OpenStax, so it's freely available, open source. I have a print copy of it. If you feel like getting a print copy to study from, I think it's like $65 and it'll be for the entire year. And it's like 1,400 pages. Honestly, you can't get a cheaper textbook that big. But you can just get by using the PDF version. I also, the first time I taught this class, I used a textbook that I like to order better. I wouldn't be using the OpenStax just because it's free. I think it is a really good textbook, but I don't agree with the order that it does some of the chapters. And so a lot of the figures too, I'm gonna pull from a different textbook I have. So this is McMurray, it's Klein. The third edition of Klein is a really good resource as well. I have a printed copy of that. One of those things where there's PDFs of it floating around if you know the right places to look online. I obviously will not tell you to go do that. But it would also be a good source to have. And I think there's probably even a couple of physical copies in the library because we did use it for a few years here. And that will go closely mirror the order that will actually go in. And we'll have some of the other, a lot more practice problems. I don't know if you've used OpenStax much before, but they're light on the practice problems at the end of the chapters. So I pull a lot of my practice problems from Klein as well, and a lot of figures and stuff. So
is it a certain edition?
the Klein is, I think the version I have is the third edition. I think he writes better. He actually got started not as a professor, but he actually wrote a book called Organic Chemistry Lab Survival Guide or something like that, that was used as like a supplementary resource to a textbook. I think he writes really well. Klein does. McMurray this is the 10th edition of McMurray, which is also weird for an OpenStax to get one that's in the 10th edition. McMurray, it's actually kind of a cool story. McMurray's getting ready to retire, and his son died of cystic fibrosis a few years ago, and so now that he is not as worried about making his mark and making money, he just basically moved his entire textbook to OpenStax for the 10th edition and just asks if you have the means to donate to cystic fibrosis research. So he's kind of doing it as a charity thing at the end of his career, which I think is pretty cool. But the nice thing about that is it means we're not getting the first edition of a textbook in OpenStax. We actually get something that's polished, pretty well built out. Some of the figures are not quite as good, but so that'll be our official textbook. Klein is also a good one though. And if you do need back to other resources, if you don't have a Chromebook or anything yet, obviously the library still has a Chromebook, maybe not obviously. They have a Chromebook lending program if you don't have your own computer. And we have at least one tutor who has taken organic chemistry over there. But if both of you guys go over to the library, use tutoring relatively.
If I need to, yeah.
If you need to. You guys met Ollie? He mostly does math. I'm not sure if he's back this year, but he actually is going into a grad school program in chemistry and has taken a lot of organic chemistry. So Ollie's really good. Brad Beaton has taken the whole series. Atticus won't be much use for this one because he bailed on us. I think that there's at least one more tutor over there that we hired specifically because they had taken organic chemistry, but I can't remember who it is right now. So there's a few tutors over there that'll help. You can always email me, come talk in lab, come talk after in the office hours. My office hours are 9 a.m. Monday through Thursday. So either 9 to 10 on Tuesdays and Thursdays, or 9 to 10:30 until Gen Chem starts. Gen Chem lab starts on Monday, Wednesdays. Okay. And you can always come find me in the Gen Chem lab too. If I'm busy, I'll tell you to come back later. But if I'm sitting around, I'm happy to talk OChem. then as well. A lot of online resources too. There's a fairly active community on Reddit, several fairly active chemistry communities on Reddit they won't do your homework for you, and if you ask, you're gonna get banned. Because they don't like that, but if you actually just need help, hey, my problem says this, I think I'm doing this right, but I'm getting the wrong answer. They're pretty good about, all hours of the day, because it's international. And so I hesitate to write, just point blank recommend, just ask Reddit. But the chemistry subreddits are actually pretty helpful. If you can't get a hold of me, or if you want a different point of view. That, and frankly, Khan Academy. Khan Academy actually got started because Sal Khan was trying to tutor his niece, who was taking organic chemistry as a pre-med. But they lived on other sides of the country from each other, so he started making YouTube videos. She started sharing them with her classmates and stuff like that. And boom, now we have Khan Academy. So really, it's really pretty strong on chemistry, especially organic chemistry. There's a lot of good stuff on Khan Academy. You can wind up getting it over your head sometimes, but this is second year chemistry now. After a month or so, you shouldn't see anything that's like way wildly over your head anymore. You will have enough background that at least the words will make sense, even if you're not sure what they're talking about. I already talked about recordings. It's just my list of questions that people always ask me when I start a class. Other just general concepts when it comes to class design. It might not seem like it, but there's a lot of effort that goes into making decisions. Even a decision as basic as, well, we're only going to have 2 tests, and that's how I'm going to grade the whole class. There's actually a lot of effort and thought that went into that. There's actually been a lot of research that shows that your work on labs and your work on homework is really strongly correlated with how well you do on tests.
Yeah.
So in classes with 300 people, it makes a lot of sense, honestly, to not grade homework. Because why grade it if it's going to be really strongly correlated with the test anyway? Yeah. Correlation is not predictive though, and some people really struggle with tests. So we're not going to structure the class that way. The class is going to have a lot of called scaffolding, basically other assignments to help build up to those tests. That said, there will be, you'll have 2 tests that'll be a total of 30% in this class. So midterm and a final, that's a pretty sizable chunk. And then we'll have weekly quizzes as well. And the weekly quizzes are basically, they're open book, no time limit, so they're barely a quiz, they're more like a small homework assignment, but it's something that that I can actually grade and give more specific feedback, and we'll go over those problems. There's always more practice problems if you want them. But the quizzes are gonna be basically like a weekly check-in. So I can continue giving you more feedback directly.
Are those then inside of class or outside?
Outside of class, which brings, I think there's another slide about it too. Basically, there's been a lot of research that shows that leaving a classroom and then coming back to recall that material sometime in the next 24 hours really helps with retention. So I think Carl did that for Gen Chem too. Did you have the weekly quizzes with Carl or not?
No, but we have them in biology.
Had them in biology. So that's the general gist of it, is basically you can't, the quizzes won't go live until 3 on Thursday. So you have to go do something else for a couple hours and then come back and think about it. And that's on purpose. I don't want you to be able to finish class on Thursday, spend 10 minutes taking the test, and then not think about it for 5 days. So they'll be done outside of class on Canvas. I'll use the auto grader as much as I can, so you get that immediate feedback, but Canvas's auto grader is kind of garbage. So on some of the things, it'll just say, you've submitted, you don't get a score yet until I go back on Monday morning and I'll grade them.
So they open Thursday.
They'll open Thursday, they'll be due Sunday night.
Due Sunday, okay.
So basically, I'm just forcing you sometime over the weekend, you've got to think about it.
Yeah.
Just so, because otherwise, in a class like this, you go 5 days without, you think about OChem for 3 days and then not for 5. Like you're gonna struggle with that, so. This is my way of forcing you to work on it over the weekends, at least a little bit, they're not typically that long.
Okay.
Usually like 10 or 15 minutes on the low end, and they might be, we don't really do any real problem solving here, but there's some, I guess we do. There's some lab type questions that might take you up to an hour.
Okay.
But not excessive,
Yeah.
and that'll be the bulk of your homework. There'll be a couple times where I just wanna give you volume of problems rather than doing it the quiz style, and it'll just be a homework assignment, there'll just be a PDF of 15 reactions that I didn't wanna plug into Canvas quizzes, cause that's a big headache.
Are they timed or can we like open it and do a couple and then leave
Yeah,
and come back to
That's
it?
totally fine. So doing the assignments, I'm not making these assignments up just to make your life difficult, right? It's there because you need to practice on specific things. We're not gonna treat this class, traditionally in this class, this is a readout class. Chemistry in general is used as a gatekeeping subject for pretty much all STEM majors for a really long time. I disagree with that approach in general, I don't think that there's any one class that should decide whether or not you're good enough to be a vet.
Right.
So we're not gonna structure it that way, especially with a really small class. It'd be great if I could give everybody A's.
Yeah.
And I have been able to in this class before. It's not gonna be like, oh, I have to give a B or I have to give a C because I need my bell curve distribution or something like that. You still see that in some of the bigger schools. I know before we offered this class here, I had a couple students who went to Davis and took OChem there, and I think it was OChem for STEM majors was 300 people in a lecture hall. And then OChem for allied health majors was 500 people. They basically, if you've ever been to is it the Mondavi Center at Davis, that concert hall?
Oh, yeah, I just.
They
did the
use that.
So I saw.
Yeah.
Some of those buildings, they're huge.
It's huge, so. Obviously, things are a little bit different when you've got that big, and they do still, there's a lot of people there that teach it like it's a hoop for you to jump through to make sure you're worthy of continuing on. We're not gonna do that this way, so as long as you do the work. Well, you'll know exactly what the tests, I do practice tests just like Carl did, in fact, Carl uses my practice test because I taught that class before him. So, I'll give you a practice test a week before the midterm, so you'll know exactly the structure, exactly what the material is, and then all I'm gonna do is change out the compounds, change out the specifics. So there'll be no surprises on those, everybody can do well if you put in the time. And unless you really struggle with test taking, in which case, come talk to me privately if you want, we can work on that. You should be, somewhere in the B range. You have to really know it to get an A, which is obviously doable if you do the studying. But it's pretty easy to get a B on my tests if you work on the practice tests and you've been doing this and stuff.
Okay, yeah, I have my SAS foundation, so I take my test.
Right, so you won't be in here. My team,
And the third person if they show up.
if they show up, first day I hesitate to assume anything. But it did not look like the Sadie that I know that has taken our classes before, so I'm trying to be hopeful that it's not a fake student, because we get a lot of those right now. They
Oh, yeah.
register and get financial aid, and then they're all AI before bots.
What?
Yeah.
That happens? That's why like
It
I
does.
all like that register and I'm like, are you still doing this? You need to register.
So that hopefully that isn't the case here. Even if that is the case though, now that we've started this class, we're offering this class. So don't worry about the class being canceled at this point. If you're not here in January,
Yeah.
it might be a little bit tougher sell. I've never offered a class one-on-one, I've done the class with 2 people before, I've never done a class one-on, that's not true. We might have to make it a special topics or something, but or make the lab special topics and the lecture regular. We would probably change the structure a little bit, make it more like an independent study.
Okay.
But it's still something that we'll try to do, because we also have people that didn't pass the 3rd quarter. And if they need to come back in the 3rd quarter, like we can't, like that would really strand them, they were planning on, now I'm gonna finish finally. And
Then we're like, no, never
we're not
mind.
offering this year. So I'm gonna try to make sure we offer the entire series regardless of any transfers that might happen.
Okay.
Sorry. I'm gonna still try to convince you that you'll be better off taking it here.
Yeah, she would be. It's my only class at this point. No, you have one other class this quarter, and then after that, I just have this. Well.
So we'll see. We'll see how much you like the class, you might change your
I mean, I
mind on
definitely
it.
wanna do it as, I don't know, I've been thinking of commuting for like 2 days a week and like staying, oh, you did that. Yes.
I mean, not to just say this because I'm the one teaching it or to bump enrollment or anything like that, honestly, it's. If your choice is 100 students or 2 students, like you're gonna get a lot more out of it and have a lot better chance of success if you can try and make that work here, even if it's uncomfortable. Or if you've already, is UNR your final destination, or is that
It's my next destination.
your next destination?
And then Cambridge for my doctorate.
Okay. So, okay. I mean, we'll work with you. You need to do what's right for you. I'm not gonna, shame you for going and doing what's right for you. But then we can have a longer conversation about that if you want to. Is there anything else here? So textbook we talked about, lab manual, I wrote the lab manual. It was my sabbatical project a few years ago. So if you have problems with the way that things are phrased in the lab manual, come talk to me. I won't be offended. It's 1st quarter especially, it's pretty well dialed in. But it's free. I'm just gonna post everything on Canvas, print it out for you and everything too. So you don't need to pay anything there. Calculator, we really only need a calculator for a couple of things in OChem. We don't do a whole lot of calculations. We do theoretical yield and percent yield. Is 90% of the calculations we'll do in this class. So, and even the theoretical yields are pretty easy because it's almost always a 1-to-1 ratio in organic chemistry. So the stoichiometry is really easy. It's just a matter of you got to do your molecular weights, and to get your theoretical yield. So, any calculator will work. Whatever you need for that. There might be a little bit of. There might be 1 or 2 calculations on the test. This first test, I might have you do a molecular weight to make sure you can do a molecular weight still. But for the most part, that's about all the calculations we'll do. Most of the problem solving we'll do in this class has to do with reading spectra and taking readings of chemicals and trying to figure out what the chemical is, properties it has. But that's all the calculations there are done by the computer ahead of time, and then you just get a spectrum that has wavelengths and intensities, and you have to figure out what that means. So it's more of a crossword puzzle than it is like problem solving, like doing conversions. Attendance, obviously I'm gonna know if you're not here, but I'm gonna take minutes. I do record the lectures on purpose, so that if you need to miss for whatever reason, and even, if there's a day where neither of you are here, or just one of you are here, I might just say, okay, I'm gonna go record the lecture and post that, and you can just watch the recording as needed. It's obviously gonna be better if you're here in person, because it's really hard to watch an OChem lecture for an hour. I probably won't make it a full 2-hour lecture if I'm just recording, just because I'll be going faster if I'm not stopping to ask questions, things like that.
If we're like sick for a lab or something, if we get the data, could we still like in?
You can.
Work?
So typically what I do in Gen Chem, this is really common, we actually have more labs in Gen Chem. Is that half of your points is for being there and doing the procedure, and half is for the write-up. We won't have pre-labs, it'll be more of a, let's do this procedure, answer a couple questions about it, turn it in. Then there'll be a couple of full-on lab reports where you have to write up your procedure. And you write up your results section and your conclusion section, so it won't be like in Gen Chem where you had a list of, here's what I'm filling out. It'll be more, it won't be like a full-on essay, but we'll practice with that a little bit so that you have some experience with that. And then we'll build on that as the quarter goes on. Your lab final will be a lab report that you write by hand.
Okay.
We'll do, in the way that that'll work is there's a, did you guys do the lemons and cloves experiment in Gen Chem? Okay, so basically we do a lab where we actually make essential oil of lemon and essential oil of cloves from lemon peel and cloves. So that would be the bulk of what we do after midterm in this in lab. So we're gonna do that for 2 weeks, 2 different ways.
Okay.
And then I'm gonna give you something that's not a lemon or clove, and you're gonna have to adjust the procedure. And then do it with something, so I've used lemongrass before, I've used 5 spice, somebody that used black pepper, turns out you had essential oil of black pepper.
It's like pepper spray, right?
It's mace, yeah, it's called mace because it's,
Did
and you aerosolize that, you. Oh yeah, somebody did that last year, I think Lex did that, last year, that was a choice by them. To do that, I would not force you to do that, basically, I'll have like, here, pick a couple things, like what seems interesting to you, somebody did cardamom, I think Jerry did cardamom last year. And then basically you'll do that test, then I'll give you a couple of those spectra that we will have been practicing on. And your job is to try and give me a plausible structure for one of the components of that essential oil. And so you'll do a lab write-up on it, you'll say, here's my spectrum, this is my information, this is why I think the structure is this. And that'll be your lab final, but it'll be totally take home, it'll be a full-on lab report, and it'll be due the end of finals week.
And those are individual.
And those will be individual, you'll each get your own unknown. And for labs with a small class, what I usually do is I'll have both of you, or 3 of you, if 3 of you are in the class, do your own setup, but then you can still work together with each other. But the main thing is I don't want just one setup between the 2 of you, because then if it doesn't work, we don't have any data.
Yeah.
At least if one of you has a lab setup that works, we get data, and you can share data if need be, but for the most part, you'll be working together next to each other on your own systems.
Right.
Which works really nicely in the fume hoods in the chemistry lab now, because there's the Ryland hood, there's the Taylor hood, you can both use your own, but you're so close enough, you could, what are you doing over there?
Yeah.
So it should work pretty well, it's worked pretty well in the past. Riley's hood and.
Right, and then Jen.
They're gonna be like that anyway, because you'll leave stuff in there from time to time, and they'll be, this looks interesting. But yeah, if we do miss a lab for any reason, with only a few people in this class, there's some flexibility, we might be able to make it up, we might, especially if you know ahead of time. We can probably, like, okay, let's get all the data for this first week, and then the second week when it's data analysis, you can do that remotely. So we'll tackle it as it comes. Yeah. Because there's fewer assignments, I don't know if I have it set up to drop your lowest score. Just because with all the multi-week labs, I think there's only like a total of 7 labs. And so then dropping your lowest lab score winds up being, plus they're not all worth the same, because some of them are 2-week labs, so they're worth double. So I'm going to be flexible with that and kind with that, but I'm not going to guarantee that we're dropping your lowest score like we've done this.
I try my best, but you know what happens when December rolls around, it's stay away. Yeah, so one of us will be here.
And we can also work out some time too, if you're sick on Tuesday, there's nobody in the lab in the afternoons on Thursday, so it might just be a case of, okay, we're gonna go outside of our normal time.
Right.
Or even come in on a Monday when I'm teaching Gen Chem lab, you can work in the hood on your own.
Okay.
On your stuff, so we'll find ways to make it up if we need to.
Alright, sounds good.
Due dates, late work, not a whole lot to worry about, turn stuff in on time. If it's late, usually what I do is 10% off per lecture that it's late. The exception being those quizzes, because if you don't do those on time, then I can't talk about the answers to the quizzes to review for the next lecture. And so if you're late on those quizzes and we start the next lecture, then it's like half credit on the quizzes. So as long as you get the quizzes done on time and then everything else as close as you can, you should be fine.
Okay.
I'm not too worried about cheating. I know you two are gonna be working together and I fully expect that at this level, whether you were sisters or not.
Right.
I expect you working together on assignments. Really, cheating really only is gonna come into play when it comes to either trying to use AI to write your assignments. Or on the lab finals and stuff like posting your lab final to Reddit for help.
Right.
I've already shown I'm fairly active, like I'm checked my assignments if I think anybody has been doing anything untoward. But just don't do that and it shouldn't be an issue. And really don't use ChatGPT because this doesn't make a whole lot of sense to you right now, but so an organic professor posted one of their homework questions to ChatGPT to see what ChatGPT did with it. And basically gave a whole bunch of stuff that makes very little sense. What the professor, if a student drew these, I'd ask them if they had a concussion.
Well, I feel like errors that are curved are never something back.
They will be for this class. So what curved arrows mean in this class, they're showing electrons moving. But if you'll notice, this arrow is not starting at a pair of electrons. And this one's just kind of starting this whole area. Like, as soon as you learn a couple of these rules, you'll realize that this is really not very helpful. And this doesn't make any sense. It's Bezier substituted. Like, there are things ChatGPT does okay. But chemistry is not one of them.
I'm pretty much an AI hater, so you don't gotta worry about that.
It's just not worth it at this point. It's especially good. I mean, AI is fine if you're okay turning in something that is like the average of the lowest common denominator. Basically, it just takes all of the possibilities and just averages them out, and you get nonsensical stuff as a result. It has some grammatical rules programmed in the case of chatbots, but that's basically all it is. It says, well, here's 75 essays that people wrote on this topic. I'm going to take their conclusion and I'm just going to throw the words in a blender and then bring it back out. So you just get the average of what other people have already done, which is fine for some things. Not if you want something better than lowest common denominator.
Yeah.
And it's really bad at chemistry mechanisms. So don't worry about that. As I find more good examples of AI being bad at stuff, I'll feel free to include those as well.
Okay. I just like to use it to help me make study sets. It's easier than going to all nights.
There's the environmental aspect of it. There are a few things where I have used AI because I was trying to totally phone something in. I knew I was phoning it in and it didn't really have any impact. I just needed to meet a deadline for administrative purposes.
Right.
And so it was a lot easier. I gave it 2 sentences and then told it to turn it into 7 sentences.
Yeah.
And it did fine with that. At least fine enough that I can turn it into my acting.
Right.
So yeah, we'll see where things go in the future, but for now, not worth it in general. Having students learn better. I always like to reinforce this. Obviously, you can't control your mood fully, but what I do like to not enforce, I have no way of enforcing this, but encourage is that when you come in here, try to get rid of any baggage that you've got going on. Use this as kind of a safe space, if you will. Like, hey, I don't have to think about that other garbage I'm dealing with. I can just go talk about chemistry. We'll try and keep it light and keep it talk about lots of real world applications. And that's, I always on those weekly quizzes, you'll get a couple points for just asking a question. And it can be something about the material we're going on. Hey, I didn't understand number 3 on the quiz. Can we go over it? Or it can be, hey, I saw this in the news the other day about chemistry. What's the deal with that? And we'll talk about it. So random questions are encouraged, but it's also a chance for you to ask questions. Anything that you still feel you need extra help with. If we do have we'll start lectures with those questions. So if there is a random chemistry application question, that's a great way to sort of cleanse the palate, if you will, when you come in here. We're just talking about chemistry now. Get rid of anything else you've got hanging over your head. I know personally that when I'm teaching especially, but even when I was in classes, I enjoyed that approach. Like I don't have to worry about all that other stuff. I've got 17 emails I need to respond to by the end of the day sitting in my inbox, but when I'm here teaching, I don't have to think about those. And I kind of enjoy that. Another one. I think you've probably both heard this by now.
Yeah.
But it really does make a big difference. Just that get rid of I'm not good at, or I'm struggling with this right now. I'm not good at this yet. Those little tiny differences, they do make a difference. And will make you a more confident person. Because really what a college degree is proving is that you know how to learn. It's not about the specific material. So if you're here to get a bachelor's degree, you've got to be good at getting better at stuff. You're not coming in here good at everything already, right? And then if you continue on past the bachelor's degree, a master's degree proves that you can learn something on your own. That you can go out, research a topic, and become an expert on it without needing help of a class, basically. And a PhD just takes that to another level. I can become an expert in an area and then discover something new in that area. Obviously, MDs, is that what you call that?
Yeah.
DVM. That's going to be a little bit different. I actually think medical doctors, DVMs and DOs and things like that, they're closer to being engineers or mechanics than they are to being PhDs. Despite the fact they both have doctor in their name, they're a very different thing.
I can go straight from my bachelor's to doctorate, so I don't need to go those other things.
But you don't need to do any research to do it.
Yeah.
The difference between a PhD and a medical doctor is the research aspect. Yeah, that's fine. It takes all sorts. I never really understood that as an undergrad, what the difference was between a medical doctor and a PhD until I got into grad school. So anyway, I always love this quote. Best things in life are free. False. The best things in life must be purchased other than with money. The best things in life are the things that you sweat for, things that you earn through effort, not money. And Starship Troopers has it. Heinlein in general is a really interesting author. If you're into classic sci-fi, he's wildly different from one book to another, what his political views are. I've read that's because he mirrored the political ideas of whoever he was sleeping with at the time. So when he would get divorced from one wife and marry another wife, his books would very, very drastically change. Starship Troopers has a lot of interesting ideas. It's also very kind of glorifies fascism a little bit more than I'm comfortable with, but it has some really good philosophical quotes too. Actually, if you've ever seen the movie Starship Troopers, came out in the late 90s, early 2000s, and it was directed by the guy who directed RoboCop, and it's totally satire, but people took it seriously. Like, this is such a bad movie, like that's supposed to be a bad, making fun of it. Never mind. So anyway, if you're interested in classic sci-fi, Heinlein's always very interesting. Alright. What time is it? Time to take a break. Let's take a 10-minute break, let's come back at 5:02, and we'll start reviewing electrons and orbitals. Everybody's favorite topics.
I have to go to the bathroom again, I drank all that coffee. Yeah. Yeah. No, that's what you plan.
How was your summer?
It was really good. Yeah, I went to New York for 2 weeks. Cool. I stayed in Manhattan. It was awesome. So my boyfriend grew up there and his family still lives there, so I stayed with them. But since he grew up there, like he knows all of the places, right?
Yeah.
So I basically just got to like walk around and not worry about anything, and he just got to take me everywhere. And it was so
Very
fun. I was there like 10 years ago, but I was a kid and I don't really remember it. So it was kind of like my first time there.
Yeah, but it's different visiting your significant other's hometown.
Yeah, it
It's
is.
very fun to.
It was awesome.
All that, yeah.
And then, yes, I am talking about. And the food is so good. That was my goal. I was like, I want to eat everything that I can.
You know, we have a couple places that are good up here, but there's
But
not
not
many of them.
And it's so convenient there. Like you can
Yeah.
literally just walk to the end of the corner and there's, that's where you don't get to walk. You're walking everywhere.
Yeah.
You go anywhere?
We went to Minnesota, see my in-laws. Always fun. It's you know, get to spend a bunch of time on the lake. Driving boats, driving jet skis,
Nice.
pulling kids on tubes, all that kind of stuff.
I got pulled on
How
a
many
tube for the
kids?
first time recently.
We have 3 now. And then
Now, you didn't have 3 as of the beginning of.
the youngest is 3, so
Okay.
he might have been a newborn when I had you as no, I wouldn't.
Yeah.
You must have been over a year old when I had you as a student. Because I took didn't have to go back to work till he was a year old. Cause I took off 1 quarter, I had 1 quarter for my sabbatical project where I was writing the lab manual here, and then I had 1 quarter that I was able to just use sick leave. To take off an entire quarter to basically just stay at home and with Kay. So. If I had you for 103, he was either not born yet or he was already born.
Little, there were a few mornings you like carried him in and I saw you.
He's definitely the baby. So we have 11, now we have an 11-year-old, a 9-year-old, and a 3-year-old. And he's definitely the baby of the phase. He doesn't talk much until he gets to know you,
Yeah.
but
There's
then
you a
he's,
little one, really blonde hair.
Yeah.
Yeah, that was it, right? But I've seen her walking around.
yeah, we have Dash is my oldest and he's in travel baseball now. He's hardcore in baseball, but he's running cross country for the first time ever because he's the middle school now. And I think he's learning to like that. The first couple practices in the first race, no, this is awful. I never want to do this. Why do we do this?
Yeah.
And then Valence is 9, so she's in 4th grade. At Bijou. She's our support. At this point, she's been practicing guitar a little bit, and she loves to be choir. She does not. She tried to dance. She doesn't really like dance.
Plus you tried Zeus.
We talked about that, huh?
Yeah.
No, we didn't get her signed. She didn't seem very.
It's
She's
similar to-
less athletic, but she is athletic, but she's less interested in doing athletic events.
Right.
She's gonna be the one who actually likes running. She will go for
Right.
a run on her own. At 9, and like, I'm just gonna go for a run right now. Just because. So I think she's gonna
That's
be the one
good.
that actually likes running and those type of sports.
Yeah.
And then Kuiper, baby, he's just a handful. Alright. Enough about all that. Let's review a little bit of a topic structure and then kind of apply it to OCAM situations. The main thing that we're gonna talk about is we're basically gonna ignore nuclear reactions for organic chemistry. You remember back in 103 where nuclear reaction, they change the nucleus. We're gonna pretend for the most part like that doesn't happen.
Okay.
So that means that the nucleus is really not as important as the electrons when it comes to things reacting. So we're gonna spend a lot of time talking about orbitals. Orbitals are the single most important. The thing that leads to the rest of organic chemistry is the way that the orbitals work. So when we're talking about how the electrons are all arranged, you might remember the Bohr model that just has the electrons on shells. It's kind of old school. I mean, Bohr did propose this in like 1900 something. But it's a decent idea, a way to look at things. And in general, we're only going to be really interested in the valence electrons. Because those core electrons, once you get a full orbital, nothing's really going to change with it. Those are so downhill in energy that they're basically stuck there. They're not going to ever change. And then just in terms of size, the nucleus is where all the mass is. An electron is, I think the number is 1700 times lighter than a proton. So even the smallest nucleus, just hydrogen with a single proton, that electron is going to be 0.0007 the amount of the weight of the proton. But the electrons take up all the space. So we say the nucleus is tiny by volume and huge by mass, and the electrons are flipped. Electrons are tiny by mass but huge by volume. So if you want an idea that the volume, if you've been to a pro baseball game, picture Oracle Park or the Coliseum, the pitcher standing on the pitcher's mound holding the ball, if that ball is the nucleus, the electrons are going to take up as much space as the rest of the stadium. So the nucleus is incredibly dense. It's got all the mass, but a tiny fraction of the volume. All right, so then this should also look somewhat familiar. S orbitals and p orbitals, right? So the Bohr model just looked at energy levels, but then those energy levels can be further subdivided. And when you divide those into smaller energy levels, the way we distinguish between them is we call it the principal quantum number is your overall energy level. So that's like your first energy level, n equals 1 versus n equals 2. And then within the n equals 2 energy level, we have these other types of orbitals. And they're not exactly the same energy as each other. The 2s orbital is slower in energy than the p orbitals. All three of the p orbitals are going to be close to the same amount of energy though. Right? Because they're the same shape, just oriented 90 degrees from each other. You picture a XYZ coordinate, XYZ, everybody's had 3D graphing, right? At least seen that before. This one's called the 2PZ because it's aligned to the Z axis. So these ones are going to be the same, just rotated 90 degrees so that this one's along the Y axis and this one's along the Z axis. Or the X axis. And I think these are actually flipped if we're following the right hand rule, but that doesn't really matter. The point is that they're identical but just oriented differently. All right, and so the way we decide where the electrons are going to go is by looking at the different energies. Right, so we'll use the official names, but you're already familiar with the basic ideas here. The Aufbau principle. Aufbau is the original German was Aufbauprinzip, because German, they like to just mash words together to make new words. It literally means building up principle. You start at the bottom and you work your way up. So you're going to fill your lowest energy orbitals before you start filling up the higher energy orbitals, right? That's what gives us core orbitals versus valence orbitals. And this is for what's called the ground state. Now you can have an excited state where you actually temporarily have an electron in a higher energy level. So for instance, if you excite one of these 2s electrons, you can get that electron to jump up to the higher energy level. And then you'll actually won't be in what's called the ground state anymore. The ground state's always what is the lowest possible energy state. And so when we talk about filling these diagrams up, we're talking about for the ground state, for the most stable state. And if you take one of those electrons and you move it to a higher energy level, you're no longer in the ground state. Now you're in what's called an excited state. Right, and so we will talk about what that looks like, but basically this is kind of how LEDs work. Is you take electrons from the ground state and you apply a voltage to it so that the electrons jump to the higher energy state. When they fall back down, they have to give that energy off some. What that usually looks like is either it gives off energy in the form of heat, but if it has to jump a significant distance, it can't exist anywhere in between those two spots, right? I said spots, but those two energies. So if it has to jump from a high energy to a low energy, it has to give all that energy away at once, which means it can't just do it by vibrating, by giving off heat. And so what happens is it creates a photon. And so that's all an LED is basically apply a voltage to make it put an electron in an excited state and then let it fall back down. When it falls back down, it gives off a photon. And the wavelength of that photon is just based on how big this gap is. And so we'll talk a lot about exciting electrons or promoting electrons when we get into spectroscopy a little bit. But that's the basic concept for right now. Wolfgang Pauli came up with the Pauli exclusion principle, which this is the simplified version, but this basically says electrons must have unique quantum numbers, so each orbital can only hold 2 electrons, and they have to have opposite spin. You can never put 2 electrons with the same spin in the same orbital. That cannot happen. And it really applies to more than just electrons. It applies to all. I always mix these two up. Fermions, which is basically the opposite of a boson. If you've heard of the Higgs boson or any terms like that, a fermion is just something that has a non-integer spin. So because electrons have a spin of 1/2 or -1/2. They can't occupy the same space at the same time. This is one of the few places where quantum mechanics actually does make intuitive sense. We know you can't have 2 things in the same space at the same time, right? That's because most matter that we're used to dealing with is fermion. If it's not a fermion, then you actually can have 2 different things occupying the same space at the same time, which is weird. Right, and then the last of these rules is Hund's rule. And Friedrich Hund basically is if you have orbitals with equal energy, you're going to put 1 electron into each space before you start doubling up. Right, so if I was writing this. So if I was looking at carbon, for instance, carbon's got a total of 6 electrons, right? There's no periodic table in here, but I see you have one there. And take my word for it. It's got 6 electrons. So we would start by saying, okay, we're going to fill up our lowest energy orbitals before we start filling up the higher energy levels. So we put 1 electron in there. We can put 2 electrons in here as long as they have opposite spin. So far, so good, right? Do the same thing here. There's 4 of our electrons. When we're deciding where to put our 2 electrons for 2p, where Hund's rule basically says we won't do that. We're going to spread them out before we double up. And they will have the same spin. Their arrows will be pointed the same way. Which that's kind of a fine point. It seems like natural course, we're gonna put them all in because I'm drawing these arrows, I'm gonna draw them all the same way because it's faster. But you actually have to, it turns out, if you have unpaired electrons, they naturally will pair up and have the same spin. They'll either both be spin up or both be spin down. And then if we kept adding electrons, and now we got to the point where we put one electron into each of these, now we can start doubling up. Alright, so this is the example that was on the other page. This is oxygen. We can tell it's got a total of 8 electrons. Alright, so we fill up 1s, then we fill up 2s, then we start filling up 2p until we run out of electrons. Right, and the shortcut we learn in Gen Chem is you just follow the periodic table, right? You just count along in the P block. Still works, but these are the rules for why that works like that. Alright, if you were looking at the different portraits, you might notice they're all white European old men. Yeah. That's because it turns out when most of this was discovered, not turns out, when this was all being discovered in the early 1900s, it turns out being white and coming from money and being either American or Northern European was a huge asset. So we can't get around, this isn't a class where we can, propose other viewpoints all that well because it's science and it was discovered by these dudes. But it's also worth acknowledging that the reason they were able to do that is because they came from privilege and they were not kind people in general. Yeah. Some of them in particular, were actually pretty good. So Friedrich Böhler is actually the first one who kind of founded organic chemistry because he accidentally made urea. They called it organic chemistry versus inorganic chemistry because they thought only living organisms could produce some of these larger carbon-based compounds. And then he was trying to come up with a new synthesis for isothiocyanate or something. And so he heated this compound up and accidentally made urea. And he said, well, it turns out, I guess we can do this in a test tube without living things, but they still called it organic chemistry. Kekule, he shows up in a lot of places, but he's most famous because he came up with the idea of resonance in benzene. He actually got that from ancient Egyptian ideas. He was reading a lot of Egyptian mythology at the time, and the concept of the Ouroboros, the snake that devours its own tail, originates in that culture from Egyptian ideas. But that would have been career suicide to admit that he actually got an idea from something in Africa. So he actually famously claimed it came to him in a dream. Had nothing to do with all these other ideas he was reading about. He vehemently denied that because if he admitted that, he would have been laughed out of professional society. Alfred Nobel founded the Nobel Peace Prize, but he was better known during his life as the Merchant of Death because he invented trinitrotoluene, which is better known as TNT, and figured out a way to soak it into sawdust and package it in cylinders. So he invented dynamite. And he always thought that his invention was going to be used for mining things, and it was, but as with most new technology, as soon as humans get their hands on it, they find out a way to weaponize it. And he actually founded the Nobel Prizes because there was an accident at one of his factories, and a giant explosion in a dynamite factory, as you might imagine, and his brother died. But the names got mixed up in the telegram. And so the London Times published his obituary, because they thought he died. So he read his front page obituary in the London Times, where they called him the Merchant of Death. And he's like, I don't want to be the Merchant of Death. And so he made something positive out of it. But he's definitely a conflicted person. And then we just have straight up awful people, like Cobb, who was very played very heavily into Nazi propaganda in that period between World War I and World War II. No, actually, it was earlier than that. Who am I thinking of? I won't get to that one. There's a lot of Germans in a lot of research that happened in the early 1900s, so we have to deal with Nazis. And that's not particularly fun, but they were very influential in a lot of this early research.
Were they like funded by the government to do research?
Sometimes, a few of them, at least one person that we will study, I'm struggling to think of who it is, was actually the one who first synthesized some of the nerve gas agents that they used in the concentration camps. So there was a lot of Germans that said, I don't like the way that this is going, like, let's get out of here and move to the US or move to other countries. Before or when Hitler seized power. But then there were some that like, no, I'm proudly German and I'm gonna help this regime. So it's a complicated history, to say the least. And like with any particular field, you have to be careful lionizing or idolizing anybody who's at the top of the game, because they have their downsides as well. One example I can think of that doesn't, if you know something else about it, then don't tell me, because I want to save this. Carl Sagan is about the nicest, kindest, smartest person I can imagine. And there's only positive stories I've ever heard from him.
He's like more recent though.
He was in the 80s, 1980s. He was an astronomer. He was Neil deGrasse Tyson's PhD advisor.
Okay.
And Neil deGrasse Tyson's a great science communicator, but I've heard he's a dick. I've heard lots of stories of him coming to speak at universities, things like that. Well, I guess it is. So, never meet your heroes, as the saying goes. There are some positive people that did really positive things, or that came from marginalized backgrounds. We'll talk a lot about Kenichi Fukui when we get into the end of next quarter. He's a fascinating story because he actually worked for the Japanese military on fuel sources during World War II. And as a result, he was kind of blacklisted by the Nobel Prize Committee for a long time. And so he actually had to wait about 30 years after he published his research before he was able to win a Nobel Prize for some really, really fundamental research that made a huge difference. And he eventually won it, only because he got nominated with a couple of Americans that published very similar stuff to him 5 or 6 years after he did. So there is a complicated history there as well. Percy Julian was the first Black PhD in chemistry in the United States, which probably means in the world. And he did a lot of really interesting stuff with medicinal chemistry, as did Chatterjee. She was actually founded kind of the area of what's called ethnobotany, which is basically taking traditional remedies from different cultures and then applying modern scientific techniques to see if there's anything there. So she applied that to a lot of Indian traditional remedies because she was from India. But that's also what led, that idea is what led to aspirin in the first place. Is they were able to look at traditional cultures used willow bark tea as a cure for headaches. It turns out that's because willow bark has salicylic acid in it. And if you take that and you add an acetyl group to it, you get acetyl salicylic acid, which is aspirin. And so they were able to say, okay, well, this is probably the compound that's actually responsible. Sometimes they come away with nothing, like there's nothing really that useful we can figure out so far, but sometimes you get some really interesting ideas. So that idea of bringing in traditional remedies into modern medicine, incorporating those ideas, is really, a lot of that came from Chatterjee. And then Marie Curie is just badass. You know about her life much, or her children? So she has two different elements that she discovered on the periodic table, radium and polonium. She discovered and named. She basically founded the field of nuclear chemistry. in a time when she was Polish, but she had to move to France to go to university because Poland didn't allow women to go to university at the time. And even when she got to France, even France being as progressive as it was, in the late 1800s, would not allow women to go to graduate school to do research. So she had to find an advisor that would kind of go against prevailing wisdom at the time. And so then she, won Nobel Prize in Physics for discovering radiation, won a Nobel Prize in Chemistry for discovering two elements. Had to leave France ahead of the Nazis when World War II broke out, and one of her daughters came with her. So she shared her first Nobel Prize with her husband, who worked in the research lab with her. And he died not of radiation poisoning, but being run over by a horse-drawn cart.
Oh.
He didn't look both ways crossing the road, and died. In her second Nobel Prize, she shared with her oldest daughter, and then her younger daughter did not leave France when the Curies evacuated to the US. She stayed behind. She was a journalist, and she actually was really instrumental during the French Revolution or resistance during World War II. And then wound up marrying one of the early Secretary Generals of the United Nations after World War II, who then won a Nobel Peace Prize. So I think her name was Irene, is the one that I think the younger daughter. Irene is the only person in her immediate family, including her husband, who doesn't have a Nobel Prize. Or was. But she just gets the consolation prize of having fought the French resistance.
Yeah.
So I always find that her whole family's life story is really interesting. This is, we already did the carbon. All right. So let's talk a little bit more about away from the history and more into how these rules work out. One of the other really important concepts that we take away from Gen Chem is that electronic systems get most stable when you can when you have all your orbitals either completely filled or completely empty. So that allowed us to predict charges, right? That allowed us to be able to predict how many electrons something need to gain or lose. So for fluorine, here's the electron configuration for fluorine. We can see pretty easily the best way to make it more stable is to do what? Gain or lose? Gain in just one, right? So when we're talking about ionic compounds or making ions, it's really easy to look at the electron configuration, be able to say, okay, I know I need to gain one electron, or I know I can just lose. Technically, fluorine could lose 5 electrons.
Yeah.
Or even 7 electrons, but that's a lot more steps. It's a lot closer to having that 2s or to be full and empty. Carbon, on the other hand, doesn't really have that issue, right? So because carbon valence shell look like this. So carbon could lose 2 electrons, could lose 4 electrons to be even more stable, but it could gain 4 electrons as well. So one of the reasons that carbon is so interesting and versatile is because it kind of has 2 directions it can go, and it's kind of equidistant from stability in both directions. Again, we don't have a periodic table up in this room, but if I just give you the electron configuration, what element would you figure it is?
Wait, no. Hang on.
We're getting into 3s and 3p now.
I counted just the top 2. That's my.
Gotcha. So you can count the total number of electrons, or which one's going to end in 3p5. You really only need to look at the highest level, right? Fluorine. And so this is what gives the periodic table its periodicity, the way that it repeats periodically, is the idea that, okay, well, fluorine looks just like this except with 2p and 2s. And then chlorine looks just like this. Bromine's gonna look like just like this except with 4s and 4p. And that's why they all show up in the same column together. It's all well and good when we're talking about ions. The trick, though, is what do we do when it comes to covalent bonds? So for covalent bonds, you might remember doing Lewis dot structures, right? Basically, the whole point of covalent bonds is if you can't actually steal an electron from something else to put it in here to fill the valence, then you have to be able to share electrons. Basically, the word covalent literally means in both valences. So covalent bonds happen when you've got more than one non-metal, when their electronegativities are close enough to the same strength, so that neither one of them can steal the electrons from the other one, so they have to be able to share the electrons. Right, and so drawing those, we won't do all of these examples, but do you remember doing this process?
Yes.
So it was figure out your valence electrons, figure out what goes in the middle. How do we determine what goes in the middle?
The one with the most electronegativity.
Both of those are correct answers. The one that's going to make more bonds, which is the one that has the lowest electronegativity.
Which is farther to the right.
More electronegative. It's the closest. Fluorine is the most electronegative. So basically, look at how close it is to fluorine.
Okay.
Right, and again, we're going to ignore noble gases because they're more.
Out of the first fluorine being formed, was electronegative?
Out of everything.
No, out of any. Okay, see how I have small written up here? Because these are the smallest.
The smaller ones are also the more electronegative ones because they're pulling the electrons closer into their core, into the nucleus. Excuse me. So I know I just said whatever's most electronegative or whatever's least electronegative goes in the middle, but there's an exception to that. Because, so if we're talking about CO2, carbon is less electronegative than oxygen, so carbon's going to go in the middle. And we get something that looks like this. We count the electrons, we wind up with a total of 16 electrons. And we just use 4 of them to make 2 bonds here, so now we have 12 electrons left. And then if we fill, since the oxygens are more electronegative, we'll let the oxygens have first dibs on the rest of the electrons. So we get something that looks like this. So now we've used all of our electrons. We done with the Lewis dot structure? This carbon's not happy. Carbon still needs to fill valence. So, but we can't just throw more electrons on there because we're out of electrons. So we basically make oxygen share more than it wants to.
Right, double.
With double bonds. And so that's a bit of a throwback because you probably haven't had to do that since middle of 102, right?
Since I had to help her.
So what about out of these two, carbon and hydrogen, what's more electronegative?
Carbon.
But carbon's going to go in the middle. Why?
But the least electronegative.
Generally,
Okay.
but here's the exception. How many electrons does hydrogen
Because
need to become
only
stable?
share one.
Because hydrogen can only make one bond because it's in the first energy level. So hydrogen, despite being less electronegative than everything else, will never go in the middle because it can't.
Right.
So generally speaking, in organic chemistry, carbon's going to be what's in the middle. And we're actually going to expand this because it turns out we can have more than one central atom. Because how else are we gonna design C2H6? That's gonna give us 2 carbons with 4 electrons each, plus 6 hydrogen, 1 electron each. 14 electrons, right? And if we try to put a carbon in the middle and just surround it with the rest of them, that does not look right. Why not?
Because just got a carbon up there and the central carbon is overwhelmed.
Central carbon's overwhelmed. Carbon needs to get to a total of 8 electrons, right? In the second energy level, you cannot go past 8 electrons. That's not just like a general rule, it cannot have more than 8 electrons around anything in the second row. So if we have 14 electrons in a total of 8 atoms, we're gonna have to rearrange this. I'm just gonna erase the whole thing. If we start by linking the 2 carbons to each other, we know this carbon can only take a total of 8 electrons. It's full once we get there, right?
Yeah.
The other carbon isn't, and we still have 3 more hydrogens. So the way we start looking at Lewis dot structures in organic chemistry is more about counting bonds than counting valence electrons. Because a carbon that's neutral has to have 4 bonds to it. If it's stable and it's neutral, carbon will always have 4 bonds. And a hydrogen that's stable and neutral will always have 1 bond. So drawing these structures in organic chemistry is more about how do I arrange the atom so that everything has the right number of bonds, rather than pick a central atom and then arrange everything else around it.
Will we ever be doing unstable carbons?
Yes, turns out that's how they react, it's when they're not stable. But we'll get there, we're not there yet. So here's the slide on that. If we assume every molecule is neutral unless otherwise specified, that also means every atom in that molecule is neutral unless otherwise specified. And we also assume every atom has a full valence unless otherwise specified, because otherwise it's not stable. So we're assuming stability with these structures. And that means that every atom, every element is going to have sort of a standard number of bonds. Carbon's standard number of bonds is 4 bonds, because it has 4 vacancies in its valence shell. It needs to make 4 bonds to get to a full valence and still be neutral. What about nitrogen? What would nitrogen look like? So nitrogen has 5 electrons, it's gonna look something like 5 valence electrons. So it needs to gain 3 electrons, which in OChem terms means when it's neutral, it's gonna have 3 bonds. So we add 3 bonds to a nitrogen. Does it have a full valence as it's drawn there? What's it missing?
It's all to the top.
So if I said draw the Lewis dot structure for NH3, this is what you would get to eventually, right?
Yeah.
And that's because nitrogen will tend to form 3 bonds because it has 3 vacancies. And if you remember doing formal charge, how do we assign formal charge for atoms? You look at how many electrons does it quote unquote own, right? And it owns 2 outright, but then it has these other 6 that are shared. So how does it own all of those? None of those? Half of them? It owns half of the ones that are in bonds, right? Because there's 2 electrons there, but they belong half to this hydrogen and half to the nitrogen. So if we look at how many electrons this nitrogen owns, we could say it owns 5 electrons, 2 that it owns outright, and 3 that it owns partially. And how many electrons did it have in its valence shell on the periodic table when it was neutral? It still owns 5 electrons, but it also has the full valence because it's sharing. Right? So when something is neutral, we can predict how many bonds it's going to have based on how many vacancies does it have in its valence shell. So how many bonds would we expect fluorine to make? Just the 1. Right? When fluorine is neutral, it'll make 1 bond. And it'll have 3 lone pairs. It owns 7 still, right? 6 outright, and then there's a pair that are shared that it has half ownership in. So it's still neutral. So instead of counting numbers of electrons to figure out formal charge, in organic chemistry, most of the time we're just going to count bonds. Anything in column 17 is going to make 1 bond. Anything in column 16 is going to make 2 bonds. 15 is going to be 3 bonds. Carbon's 4 bonds. Hydrogen will always be 1 bond. And so when we're talking about these structures, that's going to be the number 1 thing we look at. And I want to make very clear, you should never have a carbon with 5 bonds. Nothing on the second row can make more than 5 bonds, but you see the most with carbon because carbon doesn't have any lone pairs, right? So all of carbon's electrons are going to be in the presence in the form of bonds. So if you ever try to draw a structure and you wind up with a carbon with 5 bonds, you did something wrong. And that's the number 1 thing, the pet peeve of organic chemistry instructors everywhere. I'm going to be patient when you're learning these things, but that is a hard and fast rule. You can get a nitrogen with 4 bonds. But what would that look like? If a nitrogen has 4 bonds, it still can only have a total of 8 electrons, right? So if nitrogen has 4 bonds, it can't have a lone pair. What's the charge on that nitrogen now? It owns 4 electrons, and how many did it have on the periodic table? So it's missing an electron, right? Which would give it what kind of a charge?
Wait, if it's missing 1, it would be positive.
Correct. So that nitrogen has a plus charge.
So it's charge +1.
Plus 1, exactly. Because it owns 4 electrons, and when it's neutral, it owns 5 electrons.
So then in the other drawing formal charges.
Correct.
For the overall element or just for nitrogen?
So we do break it up by atom in organic chemistry. We'll say in this case the hydrogens are all neutral. The nitrogen is +1. Here the hydrogens are all neutral as well, and the nitrogen is neutral. So this whole thing, NH3 is neutral. NH4 has to have an overall plus charge. Which that was one of your polyatomic ions, right?
So, yeah.
This one was ammonium. This is ammonia. You take ammonia and you make it act as a base, make it accept an H plus. It goes from being ammonia to ammonium.
And can't it be like, not with these ones, but like the center one can have a formal charge and then one of the outer ones can have formal charge, so the overall guy is neutral, but that is the formal. The overall guy.
Yeah.
So.
So you can have a molecule like this. It's not the best possible star structure though, because if I fill in all these lone pairs. So does the carbon have a lone pair? It's positively charged. If the carbon had a lone pair, it wouldn't be positively charged, it wouldn't be neutral either, it'd be negatively charged. That carbon has 5 electrons that it owns. It's got an extra electron because it has that lone pair. So if you see a carbon with a positive charge, it actually doesn't have a complete valence. It only has that it owns, and it only has a total of 6 in its valence, even if you count the partially owned ones, right? So what could we do to make this a more stable Lewis dot structure? Yeah. Pick one of these. Pick one of these oxygens and make it share. Now all of a sudden, what's the charge on the carbon? But carbon, when it's neutral, owns 4. Nitrogen, when it's neutral, owns 5, because where it is on the periodic table, right? So, yeah, you can have some structures where you get negative charges here and positive charges in the middle. In organic chemistry, when our middle atom is carbon, that's usually going to be pretty unstable, because usually if you've got a negative charge, anything with a negative charge has to have a lone pair. If you like run a mathematical proof on it, you can't have something with a negative charge without a lone pair on it. So anytime you get a negative charge next to a positive carbon, it's always just going to rearrange like that to fill the carbon's valence.
But that would be one of those areas where guy has a formal charge of neutral, but then the individuals could have like a positive and a negative.
Correct. Yeah. You'll get there. Remember, in a lot of this, we're going to basically kind of gloss over. We're not going to be counting electrons nearly as much, because it's going to be, we're going to switch our frame of reference to think more about these atoms in terms of how many bonds do they make.
It helps that I helped her.
Yeah. You're not that rusty. You just head someone off.
I just dates, so like ammonia, and that sort of stuff. Would it be good to review those?
We're going to talk. No, the polyatomics. Some of them are going to come up again, but for the most part, we'll talk about weak acids and weak bases a little bit next week, I think.
Okay.
And we'll talk a lot about that, but it's less about memorizing the names and more about knowing how to move an H plus from one place to another.
Okay. That's
All
when
right.
we get pH.
That's when we get the pH and pKa, weak acids and weak bases, all that good stuff. All right, so here's the takeaway. Carbons are tetravalent, meaning they generally form 4 bonds. And this is true for all of these when they're neutral. If carbon has a charge, it's not tetravalent. If nitrogen has a charge, it's not trivalent. And so it's when we look at these structures, it's going to be more about what's the charge on the atom than it is actually counting lone pairs. And
But anything in the. But it says 14, but like when you're only looking at like it's 2 sections, so 4 over is gonna be tested, right?
yeah, we're not going to deal much with silicon or anything else in that region, because when we start getting d orbitals into play, things change a little bit.
So are we gonna?
Pretty much for OChem, there'll be a few reactions where we have a heavy metal or have something larger that acts as a catalyst, where we have to consider d orbitals, but for the most part, we're just going to be looking at the second row. All right, so with that in mind, one of the reasons that it's worth thinking about that is because if we have a whole bunch of let's start. If we don't specify how many hydrogens are attached, you'll find out pretty quickly as we start building these larger and larger molecules, drawing the hydrogens is a drag, right? It's a really repetitive, but you've got to be able to follow the rules and make sure that you have enough hydrogens added. So what would I didn't draw the hydrogens here. How many hydrogens should I put on each carbon? So let's look at this carbon first. How many bonds does it have? So there should be 1 hydrogen. Now it's tetravalent. Now it's stable and neutral.
They all have space, they all get 1.
So they all have 1.
And then this same food village, do I mean that you taking out the letters, the college here?
Yeah, so this is what's called the complete structure. When you actually show all of the carbon hydrogen bonds. The skeletal structure basically just replaces all the carbons with just a line. Anytime you see 2 lines coming together, that's a carbon.
But you still put your H's on, right?
No, not skeletal structure.
You assume that they're there.
You assume that they're there.
You still draw the line?
No.
No.
So this would be the skeletal structure for that compound. It's implied that all the hydrogens are there because there's no charge on anything. If I put that there was a negative charge here, that changes everything. If there's a negative charge on this carbon, that means it's got a lone pair, not hydrogen there. And so generally speaking, what you have to do with the carbons to get from the skeletal structure to the molecular formula is you have to be able to count to 4 but not 5. Okay, so if we ignore this, you just look at the skeletal structure. If you wanted to come up with what the formula is for finding the molecular weight, say, we count all the different joints in here where the lines come together. We can say, okay, well, there's 6 carbons. And then you have to go back and say, okay, on this carbon, there's a hydrogen. There's also going to be 6 hydrogens, right? And so the way the reason the skeletal structures work is because we're assuming every carbon has 4 bonds, unless it's got a charge, and every nitrogen has 3 bonds, unless it has a charge. So if I wanted to, let's see. That's a molecule called furan. What's the formula for it?
C4. H4.
Carbon, 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 so 4 carbons. That's part of the oxygen's part of the ring, but it's not a carbon. So 4 carbons, 1 oxygen. The oxygen already has 2 bonds, so it doesn't have any hydrogens attached to it. These 4 carbons all have 3 bonds, so they each need 1 more hydrogen. So basically you add, when you're going from skeletal structure to the complete structure, or to the molecular formula, you add enough hydrogens to fill things out.
Would there ever be a benzene ring where it's just double bonds all the way around, it's just all carbon?
So. Like that.
Yeah, would that happen?
If you do that. Well, so we have to talk about, now we have to talk about molecular geometries. Because
Never
what's the
mind,
bond?
never mind.
No, that's where we're going next anyway. So good question. What is the molecular geometry going to be on this carbon? What's the shape? What angles? So that would be tetrahedral, right? If it was tetrahedral.
Are we looking at just a section of it or looking at?
Just look at this carbon. That carbon is going to be, it has 4 bonds to it, but how many things are taking up space?
3.
Only 3, because even though there's a double bond there, they have to be in the same space, right? So that makes it trigonal planar, which would be 120 degrees. 360 degrees divided into 3 evenly is 120, right?
109 is only on the H2. If you're counting the lone pair, right?
109. We use carbon instead, it's got, then we don't have to go with lone pairs. When you have 4 things taking up space in 3 dimensions, you get, that's when you get that 109. That's that tetrahedral structure. So the carbon, a carbon that has 4 different things around it is going to be tetrahedral. A carbon that has a double bond only has 3 things around it. So it's going to be 120 degrees, roughly. And so all of these carbons look the same that way, right? They're all going to be trigonal planar, so this whole thing is going to be flat. If you try to do this, if you only have 2 things taking up space around a carbon, what shape is it going to try to be? Well, let's look at CO2.
Oh, because it wouldn't have a lone pair.
It doesn't have lone pair,
It wouldn't bend at all.
so it's linear. So if you try to take carbon and make a ring
Yeah.
with all double bonds, you wind up with a really, really messed up geometry. It's not going to be very stable. It's going to rearrange itself.
So I should read those.
Well, the nice thing is that if everything we're dealing with is in the second row, we only have to go to tetrahedral.
Yay! There's molecular geometry and there's another one that is.
So the electron geometry is the one where you can see the lone pairs, and then you basically so.
I have cards, guys.
So do we
Nice.
need, do we need both molecular and?
Molecular and electron geometry. So this oxygen in the furan that we were just looking at has 4 electron groups around it, right? 4 electron domains taking up space. So we would expect that oxygen to be tetrahedral. Turns out it doesn't behave that way, but that's because of electrons being weird with other electrons. We'll get to that. Turns out there's a resonance structure. It doesn't actually behave that same way. It behaves like it's trigonal planar. But we'll get to why that is later.
So, since I'm gonna be reviewing these tonight, I don't think you up to. The second part was what we're doing, right, so that's up to 10 to.
Right, so if you can only go to 8 electrons, means you can only have at most 4 electron groups. Which means tetrahedral is the largest thing, so you don't have to deal with anything with 5 electron groups, 6 electron groups.
Are we gonna use electron geometry at all?
Yeah, although we're gonna switch the way we're gonna talk about it in terms of hybridization. Remember hybridization?
Under the word.
So that's what we're gonna start talking about.
We go.
That's Linus Pauling, one of my other science heroes. He lived in Big Sur in the '60s when all the rock and roll stars from the LA area moved up to Big Sur. So he got to hang out with Bob Dylan and Neil Young and stuff like that.
Very cool.
He is the other person besides Marie Curie who has won 2 Nobel Prizes in 2 different fields. Marie Curie won one in chemistry and one in physics. He won one in chemistry and he won the Nobel Peace Prize during the '60s for his work on nuclear disarmament. And Rolling Stone sent somebody out to interview him in the '90s. And this was just a stray cat that was on the fence post, and the photographer said, "Put your arm up on the fence post," and the cat jumped on his back. So by all accounts, also just a very kind person. Actually taught his great niece. His great niece went to school here.
That's pretty cool.
Yeah. And she took chemistry with us. So anyway, we're out of time for today. Just flew by, didn't it?
Did we have lab today?
We will have lab today. Bring a computer if you have one, because it's gonna be a computer-based one. It's basically like practice drawing some of these structures on the computer instead of by hand.
Is there a format site for this? I don't have to try to draw with my mouse pad.
Correct.
Okay.
So we'll use Volview, and then when we need 3D, there's another program you can use, or you can use Volview to draw it 3D.
Is that what we use at the end of Gen Chem?
I think so. So Volview,